Hi folks, this tutorial is about error handling in C++. In C++, as in many other modern computer languages, error handling is best done with try and catch blocks. What is a try and catch block? It consists of the try keyword and your code that does some work within the curly braces, and if an error occurs and an exception is thrown anywhere here, then you catch it in the catch block and do something about the error here. For instance, you might free up some memory you reserved earlier, or unwind an incomplete transaction, or perhaps write to a log file. The possible actions you can take will depend on the type of error. Also, you might not catch or choose to handle the exception here, in which case it will propagate up to the caller of the method that contains this try-catch block. The caller might handle it within a similar catch block, or if it doesn't get handled anywhere further up the call hierarchy, then the application will terminate. Let us now look at some examples and get familiar with the syntax and the options. In the try block, I can simulate an error by intentionally throwing an exception. The type of the exception will be the type of the argument of throw, which is an integer in this case. I am catching it and printing out a message. Another type of exception I might throw is a string. Notice that the appropriate catch statement was executed, the one that matched the type of exception raised. C++ has predefined exception classes, and the most generic one is called, unsurprisingly, exception. To use these exception classes in your program, include the exception header file. Here I say always catch exceptions by reference. Why is that? The predefined exception classes form an inheritance hierarchy, and if you catch exceptions by value, then slicing could potentially occur. I will talk about slicing in a future video. For now you can Google it if you are interested. The bottom line is catch exceptions by reference. There is also a catch statement that will catch any type of exception. However, in the body of this catch block, you won't know what kind of exception was raised. There is no way to refer to it. So up here, if I throw an exception which does not have a matching type among the catch statements, then it will be caught by this generic catch statement. Now that covered the basics. The next topic is about terminating the program when an unidentified exception is caught. When an unexpected error occurs, you might want to preempt a program crash by gracefully terminating your application. You can define your own terminator callback function and set it up like this, and then execute it in the generic catch block. In this example, a runtime exception is raised, but it is not caught by the first catch statement because the domain error class is on a different branch of the exception classes hierarchy. C++ built-in exception classes cover a range of error conditions, but there may be cases when you'd want to create and use your own exception classes. The proper way of rolling your own is to subclass from exception, or one of its subclasses. Let's say my program is processing customer records, and I want to catch any customer-related errors with my own exception classes. I envisaged a custom-made exception class hierarchy in which I have a customer error exception and two subclasses of customer error. The customer error class inherits from exception. The two subclasses are for the two more specific errors that could occur, namely when a customer ID is invalid and when a customer record cannot be found. In the customer error class, I have a couple of member variables, customer ID and error message. The customer ID is initialized in the constructor. I have a getter method for the customer ID and a setter method for the error message. They are protected, so they are not visible from the outside world. They don't have to be, but they are accessible to the subclasses. I declared them virtual, thinking that I might want to override them in the subclasses. It is generally a good practice to implement a what method in a custom exception class. I am overriding the what method of the built-in exception class here, and just display the error message. The what method should not be able to throw an exception, so it is decorated with the noExcept keyword. By design, the function returns a pointer to a null-terminated character string. For this example, the customer bad ID error and the customer not found error classes are very simple. They just assign the appropriate error message to the member variable. And now onto the function where we are validating the customer ID. If it is negative, then a customer bad ID error is thrown. Now let's see how this error handling works. In the try block, I call the validate customer ID function, and if an exception is thrown, I catch it and display the error message by invoking the what method of the exception. Nothing is printed, so an exception wasn't raised. But if I change this to a negative number, the exception was caught and the error message is displayed. Let's now test the customer not found error. Again, the exception was caught and we see the relevant error message displayed. In an error message, it is sometimes useful to see in what file and on which line the error occurred. To include that information in the error message, I slightly modify my exception classes. Firstly, I declare a struct with a line number and a file name. In the customer error class, I add a location member variable and a getter function for that variable. The location is now an additional mandatory parameter for the constructor. In the two subclasses, the error message now includes the file name and the line number. Now, when an exception is thrown, the values of the line and file built-in macros are passed into the constructor. Let's see whether it tells us the correct information. And it does. Line 52 was where the error occurred. Now checking customer not found error. That is correct as well. Situations may arise when, as you handle an exception, you decide to throw a different exception while also retaining the original exception. You may want to throw a different exception if it describes or represents the problem better and you know it will be handled more appropriately further up. In order not to lose the original exception, you need to nest it inside the new exception. This example shows you how you would do it. This function retrieves and returns the account balance of a customer. Before retrieving the account balance, it makes sure the supplied customer ID is valid. When it is not, an exception is raised as we saw earlier when we looked at the validate customer ID function. That exception is caught here, but let's pretend that for a caller it makes more sense if we say that this customer could not be found. So we throw a customer not found exception, and just in case it will still be useful, we include the customer bad ID exception too. Throw with nested will do this automatically for us. At the other end, this is the code for the caller. Here we try to get the account balance, and to be on the safe side, prepare ourselves for the possibility of not being able to find the customer in the database. See, here this error handler wouldn't catch the customer bad ID exception. Being curious as to why the customer record could not be found, we go further and look deeper. On this line, this is how you get access to the nested exception, if there is any. And then you call the rethrow_nested method and catch the nested exception. This might seem like a roundabout way of doing it, but this is how it works. Let me play with this validate customer ID function a little bit. What if I changed the order of these catch statements? Even though a customer bad ID exception was raised in the try block, the handler that caught it was the generic exception. The lesson to learn from this is, if you implement a series of catch blocks, order them from the most specific down to the most generic. One other quick change here. I replaced the call to the validate customer ID function with this. The error message will include the name of the function we are in. It will be generated by this handy macro. Information like this is useful when you are trying to track down the source of an error. No discussion on error handling is complete without addressing memory leaks. Consider this example. A customer object is created on the heap. Then details of the customer are displayed. And finally, the memory occupied by the customer object is freed, just as it should. All this seems to be fine. Now, what if an exception is thrown in the display customer details function? Well, the exception will be caught, but unfortunately the memory occupied by the customer will not be freed up. Execution never reaches this line, so the customer object's destructor won't be called. So we have a memory leak. Take a look at the customer class. In the display customer details member function, we find our good old friend validate customer ID. In the destructor, a message is printed on the console for diagnostic purposes. I now change the customer ID to an invalid value. The error message is displayed, and that's good, but the diagnostic message from the destructor is missing. What to do? Well, we could do one of two things. Create the customer object on the stack, or if that's not practical, then use a smart pointer. When a smart pointer object goes out of scope, its destructor will call the destructor of the object it points to. Very often, we rely on the destructor to free up memory occupied by an object. Have a look at this joint account class. The constructor receives the IDs and names of the two account holders, and in the constructor's body, two customer objects are created and they become member variables of the object. We did not forget to free up the memory occupied by these two customer objects, so everything seems to be alright. Or is it? The problem is that if an error occurs in the constructor, then the object destructor is never executed. If an exception is raised by the validate customer ID function on the first line, we don't have a problem, because at that stage memory hasn't been reserved yet and a joint account object will not be created. But when only the second validate customer ID function fails, and we bomb out at that point, then the memory reserved for the first customer object will not be released. Now, instead of relying on my words, let's test this. Here, I'm creating a joint account object, and look, the second ID is invalid. What I was looking for was the message that the customer's destructor was executed. This message here, but there was none. The solution is to catch the exception in the constructor and clean up the resources there. We cannot rely on the joint accounts object destructor as it won't be called. See, now the destructor of the first customer object was executed. If this looks confusing on first sight, you might want to pause and spend some time pondering over this example. This basically covered the use of the try-catch block for error handling. Before we finish, I'd like to spare a few words on what I call old-fashioned error handling. It works by returning an error code from functions. A function might return -1 to signal that an error occurred. In this case, the convention is to also set the errno global variable to some error code. The system might set it, but it can also be set by the programmer. In reality, errno might be implemented as a macro or a function, but we can think of it as a global integer variable. Another alternative could be to return false on error and employ an in-out string parameter for the error message. Finally, a more sophisticated solution is to create an error struct or class and return an instance of that from the function. If you are developing a program for your own use or work in a small team on an in-house application, then this kind of error handling might do the trick, but in general, using try-catch blocks is the preferred way to go about error handling. Thanks for listening. Bye.